Hey guys, welcome. So in this video, I'm going to show you how to find the inverse of this particular 3x3 matrix, and this matrix should look familiar. Anyway, I already made a video on finding the inverse of any n by n matrix, and so we're going to follow the methods in that video to find the inverse of this 3x3 matrix. So definitely recommend that you watch my video on the inverse of any n by n matrix. Alright, cool. Now, this matrix should be familiar because it was our example on 3x3 determinants. And what we found out in that video was that the determinant of this matrix A is equal to 1. And that will mean that the inverse of this matrix A is going to have nice entries because the inverse of any matrix A is defined to be 1 divided by the determinant of A times the adjoint matrix of A. And so in this particular case, the inverse is just going to equal the adjoint because the determinant is 1, and so 1 over 1 times the adjoint is still just going to be the adjoint. And in general, the bulk of the work in finding the inverse is going to fall on finding the adjoint. And of course, if you don't already know the determinant of your matrix, then you also have to put in some work to find the determinant, which we don't have to do here since we already did that in a different video. And I'll link that video below this one. Anyway, most of the work is going to involve finding the adjoint. And in our case, all of the work is going to be, the remaining work is going to be on finding the adjoint. And here's how you find the adjoint matrix. You start with what's called matrix of minors. So you start with a matrix of minors. And then you transform the matrix of minors into what's called a cofactor matrix. Cofactor matrix. And if you take the cofactor matrix and transpose it, that is, if you take the transpose of the cofactor matrix, what you get is the adjoint matrix. So the adjoint of A starts with the matrix of minors, and then from the matrix of minors we create the cofactor matrix, and then we transpose the cofactor matrix, we transpose it, and then we get the adjoint matrix. Yeah? Okay, cool. So let's start with the matrix of minors for this particular matrix. So matrix of minors. Yeah? Okay, so for this matrix, the matrix of minors is going to require that we replace these 9 entries with the following 9 entries. And these are the following 9 entries that we need to replace these guys by. Okay, for a ruler, but it's pretty hard to grab. Anyway, let's do this. Let's draw our square brackets and we'll be on our way. So, the first entry, which is 4 right there, is going to be replaced with the determinant of A11 bar. Now, A11 is 4, right? That's the entry 4. Now, A11 bar is this 2x2 matrix, which is like what happens if we got rid of all the entries in the row and column involving this entry of 4. So if we got rid of the first row and the first column, then we end up with a 2x2 matrix with these 4 entries. And so A11 bar is the matrix with these 4 entries, -6, -2, 9, and 3. And what we need is a determinant of A11 bar. And so this 4 there is going to be replaced by the determinant of A11 bar in the matrix of minors. And so if we move in similar fashion, then this -5 right there will be replaced by the determinant of A12 bar. And A12 bar is going to be the matrix with the entries 5, -2, -8, and 3. Yeah? Okay, cool. And then finally, determinant of A13 bar is going to be the final entry here in the first row of the matrix of minors, and it will replace that -2 right there. And so here is going to be determinant of A21 bar, right? And then did A22 bar, and then did A, and then what is it? Second row, third column, so 2-3 bar. And determinant of A31 bar, determinant of a 3 2 bar, and then determinant of a 3 3 bar. Okay, so you know, use like analogous, like, you know, approaches to like 4x4s and so on. But as you can see, this is pretty tedious because each one of these is determinants. And so if you're working with a 4x4, each one of these will be like a 3x3 determinant, right? And there will be like 16 entries as opposed to 9 here, right? Because you're working with a 4x4 in that situation. Anyway, here 2x2 determinants aren't so bad. And so because these are old determinants, we know that they're just numbers. So we also additionally don't need as much space as it might appear at first sight. And so yeah, this will be enough space for the matrix of minors. And so let's start calculating them. Okay, so first is oh, I went too far up, but whatever, you get it. I meant to stop there. Okay, first is notice that a determinant of A11 bar, as we said, is the determinant of this matrix right there, that 2x2, and that's going to be negative 18 minus a negative 18, so that's going to be 0. So determinant of A11 bar is 0. And we proceed in this fashion, and if you do this correctly, you'll find that this next guy is going to be -1, and I could check, is it -1? Let's see. So this guy would be determinant of A12 bar, and so that'd be like the determinant of this matrix right there, and that'd be what? 5 times 3 is 15, minus -8 times -2 is positive 16. So 15 minus 16 is -1. Okay, cool. So I did fine. And then this is going to be -3 right here. And then this is going to be 3. You could do this more carefully, as I said. And then this is going to be -4. And this is going to be -4. And this is going to be, let's see, -2. And this spot right here is going to be +2. And then this guy is going to be 1. And I guess just like for sanity check, let's check that entry right there. So that'd be what replaces the 9. So that's a determinant of A32 bar. So to find that, we'd have to do what? We'd have to take that and take this, right? Well, my hand is getting in the way, but you get it. Like take this actually, and then look at the determinant of that 2x2. So that's going to be what? -8 minus a -10, so -8 plus 10, and so that's +2 as we claimed. Okay, so there it is, that's 2. So we're done with the matrix of minors. And from the matrix of minors, we want the cofactor matrix. So the cofactor matrix, and it's pretty easy to get to the cofactor matrix once you have the matrix of minors. Recall this quantity, -1 to the power of the sum of I and j. So for this entry, that'd be -1 to the 1 plus 1. For this entry, it'd be -1 to the 1 plus 2, and so on. And we'd already done this when we're doing determinants, so you should be familiar with this. But yeah, if we do that, then we'll get a plus here, a minus here, a plus there, a minus here, a plus, and then a minus, and then a plus, minus, and then a plus. And so the cofactor matrix is simply the matrix of minors changed by these pluses and minuses that I have put. So obviously if it's a plus, you know, we don't change the entry on the matrix of minors. For example, that -3 stays a -3 in the cofactor matrix because that's a positive 1 right there, that plus right there, because it's -1 to the power of, what would it be, 1 plus 3, so that's -1 to the 4th, which is +1, which is why I wrote a plus there, and therefore I do not do anything to the entry of the matrix of minors, because that plus there doesn't affect the -3, whereas this minus right here above the -1 changes this -1 into a +1 when we move to the cofactor matrix. So that's all you have to do to the matrix of minors to get to the cofactor matrix. So the cofactor matrix is pretty easy to get to, and in this particular case, it's going to be the following. The cofactor matrix is going to be the following. And that is, you'll see, sorry, almost done. okay, the cofactor matrix is going to be, it's going to be, well, 0, positive 0, 0. Negative 1 is positive 1, so just 1. And then positive negative 3 is negative 3. And then negative 3 here. And then negative 4. And then positive 4. And then negative 2. And yes, because it's positive negative 2. And then negative 2. And then 1. So here you are. We've just gotten to the cofactor matrix, right? Okay. Now, once we have the cofactor matrix, all we need is the transpose of the cofactor matrix. And once we transpose the cofactor matrix, we get our desired adjoint matrix. So I guess I'll write in black. So once we transpose it, we get adjoint of A. And so the transpose of this matrix will be the following, right? And let's try to create the same size matrix. And so yeah, ruler. Oh, I moved my paper a little bit. Didn't mean to. Okay, there it is. Just okay, there and there. So the adjoint, which is the transpose of the cofactor matrix, is going to be 0, 1, negative 3, right? So this row became the first column, this first row, and then the second row will be our second column in the transpose, right? So this is negative 3, negative 4, and then 4, and then finally it'll be our third row here will be the third column, so negative 2, and then negative 2, and then 1. So this is the adjoint matrix, and for this particular example, A inverse is going to equal 1 over the determinant, so 1 over 1, times the adjoint matrix, so simply equals the adjoint matrix, and that is already written above here, so no point in rewriting it. So this guy is the inverse of that guy. Now, we know that we can check that we have found the correct inverse because we know that a matrix, any matrix A, times its inverse is supposed to equal the identity matrix. And in fact, even though matrix multiplication is not commutative, in this case, we could write it in reverse order and still wouldn't matter. And since we have a 3 by 3, here we'd expect that we get the 3 by 3 identity matrix. Now, we know that the 3 by 3 identity matrix is going to look like this, right? So, if I slide a little bit more and draw it, so it's going to look like, for a 3 by 3, the identity matrix is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. All right, so let's spot check this in a couple of places to make sure that we found the correct inverse. So let's check that spot and this spot. And just using matrix multiplication, I'm going to do A times A inverse and check that this is going to be 1, that's going to be 0. So for this spot, for the 1, we'd have to take this second row and multiply it against the second column here. So that's 5 times negative 3, so that's negative 15, and then plus negative 6 times negative 4, so that's positive 24, and then plus, it's going to be negative 2 times 4, and that's going to be negative 8, and so negative 15 plus a negative 8 makes a negative 23, so I have negative 23 plus 24. That is in fact equal to 1, as we expect. And then for that 0, we need this third row made vertical against the second column. So that will be like negative 8 times negative 3, so that's 24. And then plus, and it will be 9 times negative 4, so that's negative 36. And then plus, it will be 3 times 4, that's 12. The 24 and the 12 make 36, so I have 36 minus 36, which is in fact 0. So good, so we did this correctly, yeah? All right, cool. I hope you enjoyed this, and yeah, keep watching. Lots more videos to come, and as I said, because this process is so involved and so long, especially if you don't already know your determinant, the determinant of your matrix, I'm going to offer you one other way to find the inverse of this 3 by 3. using an augmented matrix. So look out for that video. I'll try to link it below this one. Yeah? All right, cool. Keep watching. Take care.